quick check 4.1 involves a couple of different ideas, mostly dealing with solubility. So we're going to be looking at this idea here about this little solubility chart. So we had to learn how to read that solubility chart correctly, and then use the information we find to calculate the amount of solute that can dissolve in any specific solution. Okay, another idea we want to look at is, what will dissolve other things, and we talk about like dissolves like. And then the last thing we'll do is to go on and practice with our dissociation equations. So the first question says, describe a solution in which 30 grams of KNO3 is dissolved in 60 grams of water. So first off, we have to look at our graph here and say, okay, where's KNO3? Here's KNO3. So it's this line here. And it says 30 grams of KNO3 dissolved in 60 grams at 50 degrees. So the first thing we say, okay, 50 degrees, come up and find KNO3, and we're interested in that point right there, which says 80 grams. So the calculation we want to say is if 80 grams of KNO3 will saturate 100 grams of water, and that's what the definition here is. It says that the number of grams that will dissolve in 100 grams of water. So that's the saturated solution. So if 80 grams dissolved in 100 grams of water, how many grams of KNO3 will dissolve in 60 grams of water? So we want to find this number before we go any further. When we solve this, okay, we just kind of do a cross multiplying, find out that x equals 48 grams. And that's the number that we have to play with here. So the idea is a saturated solution, a 60 gram saturated solution, could hold 48 grams of solute KNO3, but we only have 30 grams of solute. So how do we describe that solution? If it can hold 48 but it only has 30, then that's an unsaturated solution. So the possible answers here would be saturated, unsaturated, or supersaturated. And in this case it would be an unsaturated solution because it could hold 48, only has 30. Okay, the next one here says, we'll describe the solution. So we're still talking about this solution here. Describe the solution if the temperature is lowered to 20. So now we've got to look at our graph and say, okay, at 20, find our line. It looks like that point. So we're talking about somewhere a little bit higher than 30. So I'd say something like 32 grams. So again, we'll do our same proportion. If 32 grams of KNO3 will completely saturate at 100 grams of water, then how much would saturate 60 grams of water? So we have to do our calculation. So when I calculate that, I get 19.2 grams. Now, here's our number that we used to compare. Okay, the solution at 20 degrees would be saturated with 19.2 grams of KNO3, but we have 30 grams of KNO3. So if that 30 grams stays completely dissolved in our solution, then we have a supersaturated solution. Okay, supersaturated means that we're holding more solute than we normally could. Now if we had a 20 degree solution, we could only get 19.2 grams of KNO3 to dissolve in it, but if we heated it up to a higher temperature, get it to dissolve, and then lower the temperature back down, then we have a supersaturated solution. Now the third question says, how many grams of KNO3 would you have to add for the solution to be saturated at 70 degrees? So again, we want to go look at our graph now at 70 degrees. And following our line, 70 degrees, way up here, it looks like we could hold 130 grams. We could hold 130 grams. Now, that is for 100 grams of water, so we have to go back and do our calculation. So if we have 130 grams would saturate 100 grams of water, then how many grams would saturate 60 grams? So let's do our calculation. Now when I do this, I get 78 grams. So we're saying 78 grams would saturate our 60 grams of water, but we already have 30 grams. So 78 minus 30 grams of KNO3, that means we would need 48 more grams of KNO3. So how many grams of KNO3 would you have to add for the solution to be saturated at 70? Okay, we would have to have a total of 78, we have 30, so 48 more grams. Now the next part is talking about different kinds of solutions, and we want to see what will dissolve with what. And we have to look at these and say, well, we're telling you that this benzene is nonpolar, iodine is nonpolar. We're telling you that HCl is polar, and we're already supposed to know that H2O is polar. So that it looks like a little Mickey Mouse, and one side is a little bit negative, one side's a little bit positive, and that's the definition of a polar molecule, you know, where one side of it is a different charge than the other side. So we have the rule that like dissolves like. So polar things will dissolve in polar things, nonpolar things will dissolve in nonpolar things. So if we want a solution, here we could say, well, let's do C6H6, that's nonpolar, and we could dissolve I2, so those two would mix really nicely. We could also say, well, water is polar, so we could say water, and HCl, those would dissolve really nicely. Now, besides things that polar and polar, it turns out that ionic compounds will dissolve nicely in water. So we could say NaCl would dissolve in H2O, and the reason is that NaCl is made out of positive ions and negative ions, and the water molecules would arrange themselves so the negative end is close to the positive ion, and on a negative ion, the positive sides of the waters would be attracted to the negative ions, and we could continue that on all sides. And so NaCl would be a good choice to dissolve in water. Now AgCl, okay, that idea might be okay, except that we know from our solubility rule that AgCl just does not dissolve. So if it did dissolve, it would be a good choice, but it doesn't dissolve. So here's our good choices here for dissolving pairs. Like dissolves like. Now the last part here is we're looking at three different kinds of things that tend to dissolve, and we want to be able to write their dissociation equations. And dissociation equations just showing how each of these compounds here breaks up into its ions. So I'm going to go with the idea that, let's say, I could put a single arrow. We could see this is going to be H+, and this is going to be nitrate. This one here is going to have H+, and F-, and etc. We can break each of these up into ions. So what we care about is how do we classify those compounds? Are they acids, are they bases, or are they salts? And the second thing, do they break up completely, or should we use a double arrow which shows that they only break up partially? So first thing here, acids, bases, and salts. We could look at the first two here and say those are acids. And we know that because acids begin with H, and we have HNO3 and HF. The second two, we say those are bases, and we know that because they end with OH-, and that makes them bases. And then the last ones here, those are salts, and we know those because they are ionic compounds, but they are not acids and not bases. So we're watching for the H's as a clue for acids, the OH as a clue for bases, and if they don't have H+ or OH-, but they're still ionic compounds, those are salts. Now, for the strong acids, this first one here is a nice strong acid, HNO3, and we just know that because we memorize. So we have a list of 8 strong acids, HNO3 is one of them. So we're going to do single arrow, just like we did, and it breaks up to be H+ and NO3-, the two ions. Now HF, it is not on our list. HCl, HBr, HI, those are all on our strong acid list, but HF is not, and so we're going to use a double arrow, and that means the HF breaks up to H plus and F minus, but those ions do have a great tendency to go together. So they break up and go together, break up and go together. So because it's weak, we use a double arrow. For our bases, we have to memorize the strong bases. And strong bases are the soluble bases. So this is actually our solubility rule for hydroxides. And we know that this is strong. So we're going to use a single arrow. And it's strong because the alkali metal hydroxides and calcium, barium, strontium hydroxide, those break up pretty much completely. And here, so we were going to get calcium 2 plus and 2 OH minuses. But magnesium hydroxide, that's not on our list, so that's going to be a weak base. And what that means is that it doesn't dissolve completely, so it dissolves and goes back together, and dissolves and goes back together. So we end up with just a few of our ions. So these two equations really look very, very, very similar, but we know for ourselves that if we wrote them in scale, this would have lots and lots and lots of calciums and hydroxides, whereas this one would be mostly magnesium hydroxides. Okay, for our soluble salts, then again we just have to memorize these. And when we do our solubility rules, we say, well, nitrates are always soluble. So this is going to be a soluble salt, single arrow, breaks up to be Al 3 plus, and we get 3 nitrate ions. And the PbI2, we have to learn from our solubility rules, iodides, chlorides, bromides, and iodides are usually soluble except for silver, lead, and mercurous. So this is one of the examples of a salt that is not very soluble. We say it's insoluble, but reality is that it breaks up a little bit, and we get Pb2 plus, and we get 2 I minuses. And those are the dissociation equations for these 6 compounds. So to know our acids, we have to memorize our strong acids. To learn our bases, we have to memorize our strong bases, and those are the same as the solubility rule for hydroxides. And for our salts, we have to learn our solubility rules. And that's how we deal with this whole equation, this whole problem.